Hey, stats folks. So we have been spending quite a bit of time doing inferences on differences, right? So taking a look at, is there a difference in the means between these two populations, right? We got population 1, we take a sample. Population 2, we take a sample. We use those sample means, okay, the difference of the x-bars, to see is there a difference between the population means mu. Now, remember what we've looked at so far have been independent populations, independent samples, right? Where one isn't going to make any impact on the other. And I think we've had good discussions trying to determine, hey, whether our populations or samples have been independent or not. Well, today is when we get to learn what do we do when the samples are dependent. So dependent, there is some sort of relationship between the two populations and the two samples, right? How one works is going to have some influence on the outcome of the others. Okay, now particularly here when we're doing our inferences on differences between these two, what we need to have is we need to have one data value in one sample matched up with, corresponding to, a data value in the other. We call that paired data. And the most common ways we'll see it out of the two ways is number one, a before and after situation. Okay, so we have something, it could be a person, right? Or it could be some sort of process, right? There's this before measurement, and then we do this thing to it, okay, possibly like an experiment, a treatment, and then we have the after. Okay, and then what we can look at is we can match up, okay, whatever it was in the sample from before to whatever it is in the sample afterwards, and they're connected, they're paired. Okay. Doesn't have to be before and after situations. It's just very common to see it in that. The other thing is, hey, if it's not before and after, at least what has to happen is they have to have the same characteristics in the two different groups. Okay, except for the one that's being measured. Everything's got to be the same except for the one being measured. Okay, and let me just jump ahead here, and I'll come back to this here in a little bit, but let me just look at our examples for today. Okay, so we can talk about the dependence thing. Our first example that we're going to look at today is a shoe manufacturer claims that athletes can increase their vertical jump heights using their training shoes. Okay. It's kind of problems roughly based off the idea of jump soles. I think those have been a thing. At least they were when I was in high school a little bit. I don't know if people are still using them, but these special training shoes that were supposed to increase an athlete's vertical. So 8 randomly selected athletes had their vertical jumps measured before using these training shoes. These, we'll call them jump soles today. Before using the jump soles, okay, then they do the training, and then after. Okay, and what makes this dependent is that the data is paired. Okay, athlete 1, there's their vertical before, 24 inches, and their vertical 26 inches from after. Okay, each data pair is connected by being from the same athlete. That's paired. Now this is an example of the before and after situation here. Okay. The second example that we're going to look at, okay, is, oops, I have a little thing there. To test to see. That sentence doesn't make any sense there. All right. Hey, to see if a new reading strategy lowers the age of when a child learns to read, researchers set up an experiment. Who did they set up the experiment with? Identical twins. Okay. You see that we can see that we've got an experimental group, okay, and a control group. Okay, remember the control group is, okay, nothing's different. Okay, that's what we're going to compare it to. And we give the treatment to the experimental group. Okay, so this isn't a before and after situation, but this is a dependent population of dependent sample anyway, because they're connected by, what's it say over here? Twin pair. So notice they are identical twins. Okay, so what does that mean genetically? Okay, right? They have the same genetic makeup. All right, they're being raised in the same home, in the same situation. Everything is the same with this pair of twins, except one gets this new treatment, this new reading strategy, okay, and one doesn't. That would fall under this bottom one here. Same characteristics except for the one being measured. Okay, identical twins are often used in different types of experiments, okay, because everything's the same except for whatever it is that we want to measure. Okay. So that's our thoughts on dependent samples there. Paired data, sorry. Lots of before and after situations, maybe identical twins, things like that. All right, so how do we get to actually working with this data? Let me look back at this example. Well, we have a before and after. And in our previous methods, what we do is we would find the sample mean of the one sample and the sample mean of the other and then subtract. Well, because these are linked, they're paired, we can actually find the difference for each data pair. So I'm going to add another column over here. Oops, that's the line tool. There we go. And I'm going to call it D for difference. Okay. And what we're going to do is we're going to subtract. Okay. Now, the order that we subtract isn't important, okay, but we have to pay special attention to how we decide to subtract, okay, when we set up our hypotheses. Okay. So what would make sense here to subtract? I think it would make sense to take the after and subtract the before. Okay. So I'm going to make a note over here that D equals after minus before. I could do it the other way, but I'll point that out when I get to the hypotheses. And so now what I can do is I can subtract these. 26 minus 24 is 2. Let's see, that would be 3. That would be 0, 1. Okay, 33 minus 35. That's negative 2 now. The negative tells us that their vertical jump actually went down 2 inches, right? And then we're 2, we're 5, and we're 3. So instead of taking the sample mean here, finding an x bar 1 and an x bar 2 and subtracting those, we can actually subtract the data values themselves because they're paired. Now, what do you suppose we do here? Instead of finding the x bars for these, we can find the average of these numbers. Okay? And what would we call that? Well, typically we'd call it x bar. But these aren't the x values anymore. So what are we going to call it? We're going to call it d bar. So we find d bar. So let me get back here to my notes here. So we look at the difference. So we pair the data. They're linked. We calculate the difference d in each pair. That's what I just did. Then we calculate the mean difference, which is d bar. Now we're also going to need to know the standard deviation of the d's, okay, so that we can ultimately test d bar. So what is d bar? Well, I'm going to grab my calculator. I'll put in the values. Oops, I don't think it's going to like that. -2, 2, 5, and 3. Quit stat, calculate, one variable list 1. Okay, now I know it says it x bar here, but I know that's d bar. Okay, so d bar, 1.75. That meant on average, each athlete increased their vertical jump by 1.75. Now we also need to know the sample standard deviation of the D's. So I'm going to head to my calculator. About 2.12. So the mean increase was 1.75 with a standard deviation of 2.12. Now what do we do with that? Okay. How do we test D? Well, with all of our tests, we need to write our hypotheses. Okay. Our hypotheses are going to look like this. The null would be the population mean of the differences, mu sub D. Okay. We have a bunch of differences, but is that all the differences? No. So D bar is the sample mean. Okay. It's the average of those differences, but we don't know what the population mean is. That's why we're checking to see, is there enough evidence to support the claim that what? Okay, that this increases their vertical jump. We are making a claim about the population mean of all the differences. So that's why I write my null as being the population mean of the differences. Mu sub D equals 0. And if that's my null, well, of course, my alternative would be mu sub D does not equal 0, and this would be a two-tailed test. Now, we could also do mu sub D is less than or equal to 0 with an alternative of mu sub D is greater than 0. Okay, just like before, we can have all of our different inequalities that we could write. Okay, we could write that pair, this pair, this pair. How do we write those? Again, we look at the claim. Now let me make one note here on what not to do. This is a common mistake. Sometimes I see people do this. They say, okay, my claim is that there is no difference in the means, and they write this for their null. And they write this for their alternative hypothesis. Okay? We are not making claims about the sample mean of the differences. We are making claims about the population mean of the differences. So that's a big no. Okay? So we write our hypotheses. Okay, that step's done. What else do we need to know to be able to do this? Well, we have to know our conditions. Our conditions are samples must be random. Now they have to be dependent. Okay, and then like normal, populations are normally distributed, or n is at least 30. Now, careful here. What's this n? Okay. Okay. Our n in this case is 8 because we have 8 differences. We have 8 pairs of data. Okay, so that n is how many pairs. It's not how many data values. It's not 16. Okay, it's data pairs. All right. So looking at this, we know the sample mean. We know the sample standard deviation. We do not know the population standard deviation. That's why this is a t-test, a t-score. All right. And we're going to calculate it by comparing, okay, how does our D-bar compare to our null hypothesis of the population mean of the D's? So it's D-bar minus mu sub D divided by, this should look familiar, our sample standard deviation, but it's S sub D because it's the standard deviation of the D's over the square root of n. This looks familiar. Also, the degrees of freedom would just be n minus 1. All right. So we've done some of the setup here, but we got to do the rest. So let's see here. Let's check the conditions for running this hypothesis test. Do we have randomness? 8 randomly selected athletes. Check. Okay. Are the samples dependent? We already talked about this, right? They're paired by athlete, same athlete. That's a yes. Okay. And then is the population normally distributed, or is n at least 30? Well, n certainly isn't 30. We only have 8 data pairs, but we do, I said it right here, assume vertical jumps are normally distributed. That would make sense for them to be. Okay, so we do have that. That's good. Let's write our hypotheses. Okay? And this is where we have to pay special attention to the order that we subtracted. Okay? Let's find the claim. A shoe manufacturer claims that athletes can increase their vertical jump. So if they increased, what has to be true about the D's? Okay. That the mean of all the differences would be greater than 0. Okay. The claim is that it was an increase. We took after minus before, so the claim is that the population mean of the differences is greater than 0. It's positive. Now let me throw a what if at you. If we had have subtracted the before minus the after, that's fine. But then what would an increase mean? What would it look like to have an increase? Well, for us to increase, if we take the before minus the after, means that difference would have to be negative instead. So take some time, choose whatever order makes sense to you to subtract, but then make sure that when you write your hypothesis, that it matches the order that you subtracted. All right, there's my null. All right, so that all looks good. Conditions are met. Let's calculate our t-score. Okay. D bar minus the mean of all the differences. Remember, we assume the null is true, so that mean is 0 over standard deviation of our differences, 2.12 over the square root of n, 8. All right, grabbing the handheld calculator for this, 1.75 divided by 2.12 over the square root of 8. I got about 2.33. Now, these are t-scores, so we know we can't use p-values, so we're going to have to use rejection regions. Who went? There we go. Right tail, left tail, two-tail test. This is a right tail test, so I'm going to set my rejection region over here. Okay. Level of significance, I forgot to say what it was. 10%. All right, so this is a right tail, 10% level of significance. Okay, we need a critical t-score, so I've got my t-distribution out. N was equal to 8, so our degrees of freedom is 7. One tail, 10%, 7 degrees of freedom, 1.415. Okay, so now I'm going to look. Where's my t-score? 2.33. Okay, well, that's definitely to the right of that critical t-score. It's in the rejection region, so we are going to reject the null. Okay. There is enough evidence to support the claim that these training shoes do increase vertical jumps. Okay, so that's our process. Okay, they're paired, subtract, find the differences, find the average of the differences, that's D bar, find their sample standard deviation. Okay, write your hypotheses, being careful to the order that you subtracted. Okay, check your conditions, find your t-score, set up your rejection region, okay, all of that. Let's look at one more example together. Okay, so here's that other one, right? So this new reading strategy, okay, to help children learn how to read earlier, okay, we've got how many months old they are when they first learned how to read. Okay, experimental group, control group. How are they paired? Okay, by using identical twins. Okay. So the first thing that we want to find is the differences so we can get the D bar. And what I did on the last one is I just did this by hand. Okay. Well, this is actually a smaller data set than the last one, but if our data sets are really big, that could be a little bit, I don't know, much for work. Let's use our calculator here. Okay, so what I'm going to do is I'm going to go into my into my lists. Okay, I'm going to clear them out first. Okay, and I'm going to put the experimental group into list 1 and the control group into list 2. I'm going to pause my video right now to do that. Okay, if you need to pause this video as well, okay, to get caught up, that's fine, but here we go. All right, so you can see again, experimental group in list 1, control group in list 2. Now we want to subtract these. Okay, and just like I said on the last one, let's note which order we're subtracting. Again, it doesn't make a difference, pun intended, okay, unless we are goofing up writing our hypotheses. So which way do we want to do this? Do we want to take the experimental group and subtract the control group, or the control group and subtract the experimental group? Again, this isn't a before and after thing here. I don't know. Let's just take the experimental group minus the control group. Okay. And when I do that, again, my goal is to find D bar and the standard deviation of the D's. So on my calculator, we are taking experimental minus control. Actually, I'm going to make a little note here. That means we're taking L1 minus L2. So I'm going to arrow over onto list 3, up to L3, hit enter, and I'm going to type in L1 minus L2. There we go. I would have to type in all these numbers anyway to subtract, so I might as well type them in at once and just have it fill in this list for me. All right, so there's my list 3. These are the D's. So D is L3, okay, which is L1 minus L2. So let's get D bar and our standard deviation. Stat, calculate, one variable statistics. Make sure you put the correct list. I'm in list 3 now. All right, X bar is negative 2.33. And the standard deviation, 2.16. Let's write some hypotheses. Is there enough evidence to support the claim that the new reading strategy, that's the experimental group, is less than the old? All right, so these are the ages, and it's that these numbers are smaller than those. Now, which way did we subtract? Experimental minus control. So if we are taking a smaller number and subtracting a bigger number, okay, we want that to be negative, don't we? We want the mean, well, that's an ugly mu. Okay. The mean differences to be negative. Okay. That would mean that the experimental group is younger than the control group. When you take this number minus that number, you get a negative. Now, just take a peek at the D bar. Notice it's negative 2.33. And think about the D's. 58 minus 60 is negative 2. Is that a good thing for this claim or a bad thing? The claim is that the new reading strategy, okay, happens at a younger age. Okay, so yeah, that would be a good thing, right? Okay, how about this one? 61 minus 64 is negative 3. Is that a good thing in terms of this reading strategy? It is. That's what we're claiming to be good. Okay, so it makes sense that the mean of the differences is negative. Okay, our null would be the mean of the differences is greater than or equal to 0. Conditions. Random. I don't know. I do not know. Dependent? Yes. Why? They're identical twins. Everything's the same except for their reading ages, which was dictated by a control group versus an experimental group. Population normally distributed, or N is at least 30. Assume reading ages are normally distributed. Good. All right, now it did not meet all conditions, because it didn't say anything that these twins were chosen at random, but let's do it anyway. Calculate our t-score, d bar minus mu sub d over our standard deviation over the square root of n is now 6. I got a t-score of negative 2.64. All right, let's set up our rejection regions. Right tail, left tail, two tail. This is a left tail test. Now, if you would have subtracted in the other order, your alternative would have been flipped. It would have been a right tail. But it's a left tail test. Level of significance, 10%. Okay. N was 6, so we have 5 degrees of freedom. What is our critical t-score? 5 degrees of freedom, one tail, 10%, 1.476. But remember, on this, it only gives positive t values. Okay. So we know that we need to take the opposite of that since it is a left tail test. We got negative 1.476. Okay. Where is this t-score that we calculated? Is it in the rejection region? Yes, it is. So reject the null hypothesis. The claim was the alternative. There is enough evidence to support the claim that this new reading strategy does lower the reading age of these children. Okay? So this is a really powerful hypothesis test for us. Okay? Paired data, it works really well for running things like experiments, right? Where you got control groups, you got the experimental groups, things like that. Anytime we have data paired, we now know how to run this test. Well, that's going to conclude the video. Thanks for watching. We'll see you later.